So
This
first of all,
conference will now be recorded.
okay, as I was about to say, these talks will be recorded, so just note that. And thank you all for coming, and thanks especially. We have a bunch of people that are going to be doing some 5-minute lightning talks today, so thank you all for those that have signed up for that. Okay, so I wanted to mention real quick that we are somewhat rebooting the cloud computing cluster that's been idle for a little while here. It's going to be co-chaired by myself, Patrick Quinn, and Zhenlong Li, who's also on the call and will be talking later. And we've reworked the purpose of the cluster to give it more of a focus on applications of data in the cloud, whereas before it was just general cloud technologies. So you can see the description of the cluster up here. I'm not going to read it to you, but the gist of it is that we are looking at partly at big data and partly at applications of a high volume of data in the cloud. So to that end, and for today's session, we have 9 speakers. I'm about to paste these speakers in the GoToMeeting chat in case anyone wants to reference who's talking or where we are. So that's now in the GoToMeeting chat. But I think we have a really good mix of speakers out there that are from, we have a couple from public sector, a couple from private sector, and a couple from academia. And I'm hoping that we have a good mix that will give us a sense of what everyone is doing and where everyone's interests lie in terms of computing against data in the cloud. So without further ado, I'm going to pass things off to our first presenter, Na.
Thanks, Patrick. Okay, everyone's seeing my screen, right?
Yep.
Yes, looks great.
Okay. Great. So I'm Na, and I will be talking about some of the work that PODAC is doing in terms of ingest and archive in the cloud. So PODAC's move to the cloud is to support the upcoming SWAT mission, but we do keep in mind of other missions as well as our existing data streams. So what we've been using for getting our data into the cloud is the Cumulus framework, which is a cloud-based data ingest, archive, distribution, and management system that can be used for all future SS data streams. And the idea is to be used by all of the NASA DAC. And it leverages AWS provided components for both efficiency in terms of processing time and cost. And some of these AWS specific components are things like AWS Lambda, Amazon Simple Notification Service, DynamoDB, and others as well. So this is a diagram of our current PODAC workflow for bringing in data into the cloud. You'll notice that there's different color coding, and that's just to distinguish between tasks that PODAC develops in-house versus the Cumulus provided tasks versus what's just provided by Amazon AWS services. So some of these PODAC developed tasks were actually built from existing code that we've already written for our on-prem data archive system. And let's take, for example, like we have a existing data handler code that we use to bring in data into our on-prem system. So what we've done is we've updated it so that it can be run as a Lambda for use as metadata extraction. So that would be like the extract metadata here box in our in this workflow. In terms of auto scaling, we define custom metrics to build on the built-in AWS alarms. So what we've done is we'll write a Lambda that calculates and publishes custom metrics to CloudWatch. So that way we can scale our EC2 instances based on the number of workflows that are in the queue. And it could be any custom metrics that we define in the future as well. that fits our needs. In terms of disaster recovery, so we need to be able to recover data in the event that somehow we lose the data either by operator error or something else. So what we've done to handle disaster recovery is we update our workflow to send a copy of our level 0A granule into S3 Glacier. And for the case of SWOT, we will only be sending our level 0A into Glacier because we can invoke our SDS provided services, which is also running in Amazon, to regenerate higher level products. So we for like level 1 or 2 products, those will be regenerated when needed. In terms of recovery, the design is to really, it's a simple design to just allow, in the case when we need to recover our level 0A, we'll just copy the copy of take the copy that we have in Glacier and then copy it back into our archive S3 bucket. And that eliminates the need of having to actually take the granule and run it through our ingestion workflow again. Of course, so the final step is that we need to somehow distribute this data to our users. So what we plan to do here is we will be integrating the egress application provided by NASA's NGAP team, and that allows the throttling of access to our S3 buckets to control costs, and it will provide native AWS feeds and redirects to the object if it's in the same AWS region. And in the end, what we get is we're going to use the CloudFront distribution endpoint to give that. That's how our users will access the data that's stored in S3. And I think that's my last slide, because since I only have 5 minutes, I don't know time-wise how I am, but that's all I have.
All right, you are actually perfect on time. So if we can pass things over to Mike Gangle.
All righty, I will try and nail that 5-minute timeline just like Na did. So I'm also from PODAC. So I believe you guys can all see my screen now. I'm also from PODAC, and we are a distributed active archive center, which essentially means we get NASA remote sensing data and we make it available to our users. So Na just spoke about the ingest portion, and I'm going to speak more about the tools and services portion. So one thing that we found out quickly when moving to the cloud, or just all of the tools and services that we've been building throughout the past 25 years at PODAC, is the further away you get from the data, the more customized or the applicability of what service you're developing kind of diminishes. So this is really important when trying to think of things that are supposed to enhance a broad swath of users. So somebody keeps asking to be made the presenter in my chat box. I'm just going to keep presenting if that's okay. So yeah, as we get closer to the data, it's very, very useful, and all the services we're building are generic. As you get further away, these become more highly customizable. Science exploration systems, performance considerations come in, and then there's this interdisciplinary measure that becomes important for the science. So what does this mean? This means, the closer the data, we want to bring the type of services and tools that we have existing in our current PODAC system on premise to the cloud. So this includes the download, search and discovery, subsetting, visualization, portal and mission pages. What this ends up looking like is a migration path. And the first thing we kind of did at PODAC was we just started lifting things in. So we bring, some services in. We just bring them as Docker containers. We set up a Docker machine and we have them running, and then we see what we can do with that and how is it performing. Does it really bias anything in terms of cost or performance? Then you start looking at all the the cool things that Amazon has to offer, like the IAM roles, CloudFront, different web services, ECS, and then their Docker services that they host, such as like ECR and ECS. And you get really good at building some of these things, then all of a sudden Amazon's going to release something new that just kind of makes you lose your mind. And there we go. You just kind of have to do it all over again, or you find the value add with this new service and you go from there. So that's a lot of what we've been seeing with our use of Amazon in our tools and services. That next step is to make the data more useful or provide some more exploration. So we do a couple of these things with our on-premise solution, but not nearly as much as we'd like to. Things such as regridding and reformatting and interpolation can really be time intensive, and the amount of resources that we have just kind of sitting around for users to use and do some of these things is not there. So it's hard for us to set something like this up on premise. And so what most of our users end up doing is they download it and they do all these things themselves. With the move to the cloud, we can be a little smarter with how we optimize things and how we bring up services and how we use resources to fulfill those services. So we have a bit more chance to do some of these things that really make the data more useful for a user right out of the box. I mean, this is important because when you talk about SWAT and some of our other upcoming missions, we have 60 petabytes over the life of the mission, and a user just can't download all that and figure it out. So we're trying to make the data more useful and leverage that scalability. Some of the pros of this is it doesn't really have to look like the cloud to user. These can be applications and workflows that they set up from their browser or can run a command line. And these should be ready to use out of the box. Some of the cons that we were running into here are the costing of these. So, billing and estimation issues. And then the concept of baseline of performance is what you can afford, not what you can provide. And then lastly, we have that far right arrow. It's, these people doing highly customized, and science and performance is becoming a big thing, and interdisciplinary data sets. So instead of trying to build a single service that does all of these, what we really want to do is enable these analytics. So never limit what a user can do, but quickly leverage newer existing tools. So I had a couple called out there. So SDAP, Google Earth Engine, Pangeo, PodPack. We know users are using these things. And so we, instead of reinventing the wheel, we really want to just make sure that users can hook our data and their transform data into these pipelines for themselves. I think that's it for me, actually.
All right, another one that's pretty much spot on in terms of time. Okay, next up is Jeremy Fisher.
Yep, I'm here. One moment. Let me grab screen share. Whoop. All right, can you see my slides?
We see a blank white screen.
Awesome. How about now?
Still like
No difference.
Awesome. Let me try it again.
Yeah, it's good now.
How about that?
we see them when you're not in presenter mode.
Awesome. That's just fantastic. Thank you, Macintosh.
Jeremy, it's up right now.
Okay. For the sake of time, I'm just gonna stay in non-presenter mode, and we'll just all hope for the best. Anyway, I'm Jeremy Fisher. I am a manager on the Jetstream Science Cloud. To give a little bit of background, so there have been a lot of different funding areas for the National Science Foundation, typically for HPC, traditional HPC, and then it kind of phased into experimental clouds, like with Cloud Lab and Chameleon, and then it went into production clouds. So Bridges and Jetstream were the first two that came on the more of the production cloud grants, with Jetstream, with Bridges being a hybrid cloud of hybrid and HPC, and then Jetstream being a pure cloud environment. So what we are is we are the National Science Foundation's first production science and engineering cloud. We focus on a broad ease of use interface, making it more accessible to more users. Part of our charge from the NSF was bringing folks that had kind of been left behind by HPC or maybe didn't need HPC or felt they didn't need HPC and had workloads that were larger than they could run in a small lab environment or on local servers. We also provide a more interactive environment than one typically finds for HPC, as well as a normal, long-running job sort of environment. And then in addition, on our advanced side with the API, we have what we like to call programmable cyber infrastructure, where people can kind of build what they need, be it virtual clusters, be it private networking to do different workloads, be it Kubernetes, whatever you want to do. We try to make the ability to do that available to people. The who, so since it is a cloud environment, we are limited per node. So our current architecture is anywhere from 1 core to 44 virtual cores. We cater to folks that are designing their own software. They need to have full control over an environment. We also cater very much to science gateway folks that are trying to make infrastructure that is broadly accessible via web, typically to a lot of different users. At present, we tallied that up this week, and we are serving about 24,000 gateway users presently. And then also to STEM educators, so folks that are teaching on the various sciences subject, whether it's for a course or whether it's training the next generation of researchers. Education and training is a big part of who we are and what we do. To kind of give an overview, so we have 2 separate clouds. One is in Bloomington, Indiana. The other half is in Austin at TAC. And then we have a small development cloud at University of Arizona for our atmosphere developers. It's all linked up via internet too, with the ExceedNet as our sort of backup network. So we have nice fast links between everything. To kind of give a platform overview, so you see the racks down at the bottom, which is a pretty accurate representation. We're running OpenStack we're backed by Ceph. Sitting on top of that is Atmosphere, which is our GUI interface. We are connected in through Exceed, which is again part of the mandate from the National Science Foundation. We do authentication with Globus, and then 90% of our users come in through our web app, which is what we show at the top there. The other 10% of our users come in typically through the OpenStack API. So they're doing things like gateways or doing more advanced things like Kubernetes or other services like that. Interestingly enough, while 90% of the users come in through the web app, the actual usage in terms of compute time is about half and half. So the folks that are coming in via the OpenStack side are definitely our power users. So this is just a quick look at the Jetstream interface. So when you first log in, you'll see a nice dashboard. It gives you the 3 big buttons there to do different things like launching instances or getting help or adjusting things. Under that, you see the allocations via Exceed and how much is used. So you can kind of get a quick look at the resources you're using on Jetstream. If you scroll down, which you can't since it's a slide, you can see how many cores and how much memory you have in use, volume space you have in use, etc. So that just wanted to give a quick look at what the web interface looks like, since most people come in that way. Did a breakdown of folks using Jetstream, and these are just sort of key areas. These are not all of the different disciplines using Jetstream. One of the things that will be of interest is Earth Sciences is one of our growing areas. We've had a 37% increase over last year in allocations in the Earth Sciences areas. It's most certainly growing. We have a lot of folks coming in through our partnerships with Unidata and UNAVCO and IRIS and folks like that have been working with us for quite a while. So we end up with more and more other users of that type because of these partnerships. One of the things we like to talk about is Jetstream for engineering. So we do have MATLAB and Simulink available via our site licenses. So folks coming in don't have to bring their own licenses. If they have workflows that are already using MATLAB and they need to scale it up, we give them a nice way to do that. Again, one of the things we really like to talk about is Jetstream for education. We do have a lot of courses that use it. We've served over 1,000 students in various environments. we, like I said, doing courses and training the next generation of researchers. It's a very big part of what we do and something we very much encourage. Being able to have a uniform environment for folks to work in, where you don't have to worry about what kind of laptop they have and what they can run, and if you're going to run into Python issues or anything else. So it gives a nice way to do education. Some usage highlights. Oh, and there's a nice typo. 414 projects currently, 73 fields of science, 207 institutions. One of the things we do like to talk about is, again, part of our charge was bringing new folks to the table. So 80% of Jetstream users have not used any other Exceed resource. So they haven't been using the national CI. So that's part of our mission with the NSF and something that's very key to determine. Again, talking about our education allocations, our gateways, we've allocated 190 million core hours since we started tracking it in June 2016. So we're trying to make a lot of compute available to a lot of people. Getting access is easy. You can get a trial access, which is very limited in what you can do, but you can have that pretty much now easily. Anybody who is staff or faculty can get a startup allocation, get 50,000 to 100,000 core hours, basically for about 5 minutes of your time of filling out a form and giving us a paragraph of what you're doing. And then you can move on once you've kind of figured out if Jetstream will work for you. You can get millions of core hours by going to a research allocation. And that's something we can help with as well. The where can I get help? wiki.jetstreamcloud.org is our documentation. Jetstream-cloud.org is our website, and these slides will be up there as well as many other slides from their presentations. It's a lot to cram into a 5-minute talk. This is what I like to call our NASCAR slide, so all of our partners, and then the ubiquitous question slide. I think I made it into my 5 minutes.
All right, thank you, Jeremy. Let's move on real quick to Julian.
Okay, can everyone hear me and see that kind of arc diagram?
Yes.
Okay. So I'm Julian Chastain, and I'm from Unidata. Many of you probably know Unidata due to the technologies that we produce, such as NetCDF, the LDM, the TDS. And just like everyone else, we wanted to start having a cloud presence for cost savings, perhaps, and hopefully to do an entirely new kind of science as well. So we started, let's see here. I'm trying to move forward on my slides and I can't do it. Maybe this way. Okay, got it. So we started Dockerizing our technologies such as the LDM and the TDS. And of course, we needed a place to deploy these technologies. And so we initially got a grant on the Azure cloud, which was wonderful. It was an in-kind grant, but the problem with those Azure grants is that they're time limited, so they don't offer any long-term continuity. So then we applied for a grant on the Jetstream cloud, first a startup, then a research allocation. I think we may have been one of the very first teams to get a grant on Jetstream. And we started deploying some of the technologies that I was just talking about, such as the Threads data server. And we were kind of duplicating what we were doing at Unidata on the Jetstream cloud. So we have a TDS here at Unidata that distributes large quantities of NCEP data. Well, we did that on the cloud with Docker, with Jetstream VMs, et cetera. And so that's great, that's interesting, but it's just kind of a duplication of what we're doing locally. So there's not necessarily a lot of new things being done there as of yet. Then we started doing entirely new things in the deployment of our EDEX AWIP server to serve the AWIPS community at our academic institutions. The EDEX server is running on Jetstream. We don't have any duplicate locally here at Unidata, serving Cave clients in our academic community. In addition, in partnership with the Big Weather Web, we've been distributing Nextred radar data, a long archive of that, and partnership also with Amazon. So the deal there is that the data live on Amazon. but they're being served by TDS on Jetstream to anyone who wants the data. The pipe between Amazon and Jetstream is free of egress charges, and likewise for Jetstream. So that's wonderful for our community. They don't have to pay a lot of money to get that access to that data, that long 20-year archive of data. In addition, more recently, we've been getting into the Jupyter Hub space along with Kubernetes and a technology called Zero to Jupyter Hub, or project called Zero to Jupyter Hub, to have a number of different notebook projects. I'm going to try to switch to my web browser here real quick if I can. Can you see my web browser?
Yes.
Okay, excellent. So we run a Jupyter Hub server on Jetstream with a number of different notebook projects that we developed here at Unidata. For example, this notebook gallery project that has this Go16 visualization notebook where you can go and visualize Go16 data in true color. All the environments that are needed to run these notebooks have already been pre-configured. You may have to select the right kernel that corresponds to the notebook project that you're running in. For instance, a notebook gallery, you want to be in that kernel. I'm going to be making this a little bit easier here soon. In addition to that, everything that we do, this is done, by the way, in collaboration with Andrea Zonka at the San Diego Supercomputing Center and ECSS, Exceed ECSS. In addition to that, everything that I've been talking about is on GitHub and is very well documented at this GitHub repo. There's numerous READMEs to explain how we set all this up. This is a diagram of all the VMs that we have running on Jetstream, or at least some of them. We actually have more than these, but this is a good high-level schematic. And finally, a lot of this information is categorized or grouped under our Science Gateway website, which is just really a pointer to a collection of resources that I've just been describing, such as the Jupyter Hub, such as the Threads data server, such as the Next-Red Radar server, such as the AWIPS EDEX server, etc. So that is what I have. I don't know if I'm in the right time limit, but hopefully I am.
All right, perfect. Yes, thank you. And we'll move right on to Anna Prevet.
Okay, thank you. Just a second, put this up. Can you see my screen?
Yes.
Yes, looks great.
Great, thank you. Yeah, well, thank you so much for the opportunity. Although I've been involved with ESIP for many years now, I don't think I overlapped with many of you on this group. Only a few names I recognize, but in any case, thank you. I would like to take this opportunity just to share with you a program that Amazon has launched recently, more specifically last December, called the Amazon Sustainability Data Initiative. And the reason why I think this might be of value to this community is because we are, as a joint effort between Amazon Web Services and Amazon Sustainability, we are trying to promote more innovation and problem solving for sustainability by working on things that are really related to the work you guys are doing. So let me see if I can make this work. Okay, I'm having the same problem of, okay, there you go. So what exactly is the Amazon Sustainability Data Initiative? I'll tell you, I'll break it down in a few seconds of exactly what we're doing. But the idea here is to, in a way, democratize access to data and to compute so that we can create more sustainability insights in general to help us not only manage our planet better, but also manage the impacts that the environment can have on our assets and our processes and the activities that humans are doing on Earth. So we are very excited with this effort and opportunity because really this is a chance to leverage the capabilities, the infrastructure, and the scalable technology on AWS and apply it to this theme that a lot of us are passionate about. So, and just as a side, I'm an environmental engineer by training, so I am a little bit biased in this space. But what is that exactly the Amazon Sustainability Data Initiative doing? How we can help? We work around three main core areas. One of them is focus on delivering big data and data in general. It's just that the cloud is particularly appealing if you have huge data sets and you want to provide better access to those, as many of you referenced today. But what we do is actually work very closely, not only with AWS customers, but also with the broader community to understand what are those key foundational data sets that a lot of people is using or would like to use, and what are the pain points and challenges that they are experiencing. And once we identify those data sets, we try to the extent possible to work directly with the data providers of those data sets, and we offer to host them in the cloud and making them publicly available to anyone that want to access the data. And so we're doing that as part of a program that has been around on AWS for a while called the Public Datasets Program. We're just giving it like a sustainability lens and creating a sub-catalog that is focused on sustainability, so it's easier for people to track those resources. So some of the data sets that we have in the system that anybody can access now and use, I have a few listed here, but it spans anything from weather observation and forecast to like ocean and hydrological data, air quality, and so forth. We have currently about 46 data sets tagged under sustainability and many more that are more broadly if you are interested in checking the registry. I have a link at the end. The other one is recognizing that although the data is a core part of all of this and is really important for people to have easier access to the data, we need to provide access to the compute as well, right? And that's very logical for all of you that are working in this space, but the reality is that we still encounter a lot of people working in the space of sustainability that are seriously constrained by the resources that they have to access data and analyze it and extract insights that they can use for decision making. So the idea here is that we want to basically make that available for anybody that wants to prototype or experiment with ideas related to sustainability in the cloud. So we have a series of different cloud grants that enable you to do that. So again, I'll share a link later, but if anybody is interested in that, we only request a small proposal. It's fairly simple, and so it doesn't have a cap. It really is based on what you're trying to do, and we work with you to figure out how much you need to do what you're trying to do. Okay, and just an example, this is one of the projects, for instance, we are supporting in the space. It's a CalAdapt. I don't know how many of you are familiar with this project out in California. Is actually a joint activity between many different groups, but funded by the Energy Commission. And what they're trying to do is provide better access to data, but also information. So they analyze a lot of data and extract knowledge that they make available to the community for them to understand what are the possible impacts of climate change, how can they better prepare and adapt to those impacts. So it's a very powerful tool, and they benefit from the scalability of the cloud as they're trying to make their resources accessible to more people. So it's one of the things that they are experimenting. Okay, and the last one I wanted to mention is as part of all this process and as we're trying to promote more innovation and problem solving for sustainability, one of the things that we recognize is that there's still a lot of barriers for people to leverage the cloud and all these huge data sets and extract the knowledge we need. And so we're really trying to promote as much knowledge exchange as we can. We do that in many different ways. One of them is we created a community of practice inside of AWS focused on sustainability, and we work very closely with those more pioneering customers. They are working in this space to write tutorials and tell their stories and what are the challenges they're facing, how they overcame those, and sometimes how they did not overcome some of those issues, and make that content and information as available to the broader community as possible. So this is just an example of one of the stories, and I'm going to skip. But I just included in this deck of slides several links that might be of interest to this group, not only to request credits, but also to look in number 5, you have cases of data in action. We have a lot of stories of different work that is being done in the cloud in this space, and that hopefully will help people and see what's possible. And the last final thing I wanted to say is we are actually hosting a couple of sessions at the summer meeting. One of them is in data optimization for the cloud, which is a little bit actually more broad than just what we're doing specifically with this program. But the idea here is it's actually a continuation of the same session we had last year, where we're trying to assess the pulse of this landscape, right? What is happening in this space? Are we seeing any emerging best practices, best ways to host data, and tools to make this data analysis ready for the community? And then the other one is more focused on actual applications for sustainability in the cloud. So that's it. Thank you very much. And I'll give it back to the presenter, the next presenter.
All right, thank you. On to Andrew Pawlowski.
Okay, can you guys see my screen?
Looks great.
Awesome. Okay, so I want to talk to you very quickly within this 5 minutes about archives of convenience in the cloud, and specifically one proof of concept application we made around dynamically creating those. I want to start off quickly by articulating something that I think is well known in our community, but is really going to be the basis of this exercise. What you're looking at here is some L2 data from MODIS. This is aerosol data from the Aqua satellite, it looks like. And really what each of these separate granules represent are files sitting somewhere on a DAX server. And so depending on your area of interest, you can get unlucky and have to pull a lot of unnecessary data when really you're only interested in a small subset of that. As we know in Earth science and Earth observation data sets, these files can be very large. This problem is compounded when you have time series data. So you have to pull a lot of unnecessary data for each point in time of your analysis. So this, really the takeaway from this is that the monolithic data access techniques are inefficient in large scale analyses. And really what monolithic data access means is like, I pull an HDF5 file off of a server and then I do something on my local machine. My slides aren't advancing. Okay, well, the question was really like, how do we more efficiently access data that's stored on a remote server? For the context of this talk, I'm going to refer to ZAR as a solution here. This is a file format. You'll see other options like cloud optimized GeoTIFFs or Parquet or ORC. But really the idea is, can we pull only the pieces of the files that we're interested in as needed? And so the way ZAR does that, this is a bit of a simplification, but ZAR has multi-dimensional arrays that are saved in discrete files. And so if each chunk is an object, you could keep them remotely on S3. And instead of pulling the entire scene down, the entire granule down, you can pull only the pieces that you're interested, either for your area of interest or maybe some time period of interest. The idea is that you're dynamically pulling instead of pulling those three large granules. And like I said, ZAR isn't the only way to do this. There are a lot of other similar methodologies. Really the takeaway is that there are context-specific advantages to interacting with data in those particular formats. But there is a lot of existing Earth data that is sitting around the world on FTP servers and other cases as large netcdf files or HDF files where you still have to pull everything down. So is there a way we can interact with those in the cloud native ways, but still not have to recompute the entire data set in every iteration of access methodology? To test this out, we had a proof of concept we built last summer called SatCat. And what SatCat did was take the corpus of GO16 full disk product imagery, their L2 product. At the time, that was about 20 terabytes of raw data. I think, well, I mean, obviously it's larger now. I don't know what it is. But the exercise was to create on-demand archives of convenience, AOCs, from those original netcdf files. And that was possible, one, because NOAA participated in the public dataset program. So these netcdf files are sitting on a public S3 bucket, and that was hugely helpful to us to be able to interact with the data in the cloud. And the second piece was that Spot EC2 instances are so cheap that the question of whether we can launch an army of instance and make some mass computation on the entire data set isn't so crazy anymore. We built out part of SATCAT was building out a novel interface. And what we did was build out a high definition video from that corpus. And so we built this imagery and strung it into videos from that 20 terabytes for like $20. It was a very cheap process because of spot EC2 instances. But anyway, what you're looking at here is Hurricane Maria. And the idea is that you would use this interface to scrub through the data that you're interested in and have a start point and end point. And then you can stage that data in the file format you're interested in. So in our case, ZAR, you can stage it. And behind the scenes, that kicks off this archive of convenience creation. And in typical cooking show demo format, I have an example already here. But the idea is SATCAT takes those netcdf files from S3, and then it builds out a ZAR archive and gives you a dedicated S3 bucket to access that data. And so you have this ephemeral, it'll last for, I think, 7 days, data that's projected in the format you'd like so that you can interact with that in that cloud native way. And so really that was the extent of the exercise. We found that it was achievable because, again, spot EC2 instances are very cheap and the data was very easy to interact with in S3. I think going forward, we're probably going to see if we can store the computation graphs and let users perform that transformation themselves when they import the data. And I think actually if Joe's going after me, that might be a good transition to that.
All right.
Okay.
Thank you, Andrew, and Joe is indeed going after you. So Joe Hammond is up next.
Great. Can you hear me?
Yes.
Okay. I joined a little late, so I didn't catch how to. Oh, there you go. Now you're sharing. Share my screen. Perfect. Can you see my screen? It looks like you can.
Yes, it looks great.
Okay, cool. I'm gonna see if I can get. Sorry, we need to minimize something here. There you go. Okay. So hi everyone. Joe Hammond. I'm a scientist at NCAR, and I work on the Pangaea project some of the time. So what is Pangaea? It's a community platform for big data geoscience. That's kind of our broad definition. And today I'm going to mostly talk about what does Pangaea mean on the cloud, and specifically with relationship to our Jupyter Hub deployments that we have on the cloud. So before I get into all of that, I just want to say that the Pangaea project as a whole has like a whole bunch of stakeholders, you know, NSF, NASA, EarthCube, funding agencies. All three of the major cloud providers have provided credits for us to try these things out. And then there's a whole bunch of institutions that have people working on some aspect of the project. So the Pangaea architecture diagram looks something like this. And we've heard or seen elements of kind of all of these in previous talks, but the basic idea is that a end user will access some large computing infrastructure through a web browser. And in our case, today I'll be talking about Jupyter and Jupyter Hub. So Jupyter is a web-based interactive computing environment, and we can host the actual computation that's done in a Jupyter notebook or in a Jupyter Lab session on a cloud or HPC system. And on that HPC system, we can have lots of compute and software that can take advantage of parallel computing generally. And so here I'm calling out Dask and Xarray as two Python packages that can do that. People also use Spark and other languages that can be accessed through Jupyter. And then the common way to describe the storage piece is that distributed storage is necessary when you have large data archives. And so on HPC, that might be some fancy parallel file system like Lustre or something. On the cloud, we think of that as object storage. And the common thread is that we can read data at very high aggregate bandwidth. And something we've put a fair bit of effort in is to talk about analysis ready data. And so ZAR has been part of that. We have a repository, the Pangaea data store, that has a catalog of data that we're storing either Google or Amazon object storage that is full of ZAR data sets that are easily ingestible into interactive data pipelines. So this is what the architecture looks like. Most of what we do is in the scientific Python space, and so our focus has really been on improving the Jupyter, Dask, and Xarray integration and making sure that those three play well with the rest of the scientific Python ecosystem. It's important to say that the three packages I just mentioned and ZAR and the things that I'm calling out as kind of highlights are just some of the options that are available. On HPC, we tend to still use NetCDF and HDF. And so you can really build your own Pangeo. And so the cloud deployment concept within Pangeo is just kind of one collection of these options. So we put these Jupyter hubs in a bunch of places on HPC systems and on all three cloud vendors and on Jetstream and OpenStack. So these things can go anywhere. On the cloud, we use Kubernetes, which I'll talk about a little bit here. So Kubernetes and Zero to Jupyter Hub is kind of the backbone of how we deploy Pangeo on the cloud. We can use any form of authentication to anything that uses OAuth 2, like GitHub or Google or Globus. The storage, we often use like an NFS home directory space and then put most of the data in object storage through some data format like ZAR. So the stack ends up being something like Zero to Jupyter Hub, Jupyter Lab for the actual user interface, which a picture of that is shown on the right here. And then for distributed computation, we use Dask and a plugin for the Dask project called Dask Kubernetes, which actually interacts directly. And so the user can actually control the amount of compute available in an auto-scaling Kubernetes cluster through a little widget that's shown down here at the bottom. So I have a link at the bottom. You can try this out. This is, we have some sample data from the forthcoming CMIP 6 data archive. And a interactive demo that actually runs on Kubernetes that you can try this out at. And I think that's all I have. So I'll probably just stop there.
All right, great, thank you.
Yep.
Next up, we have Peter McGarry.
Sorry for that. Can everybody see the slide deck and hear me all right?
Yes.
Okay, thank you. I just want to thank Patrick and Chris for inviting me to this forum. I'm going to share with you the NDE Proving Ground, which was a study funded by Noah Nestis to look at migrating their ESPDS near real-time operational systems up into the cloud. The effort was funded by an OSGS study to look at creating an enterprise product generation framework that could support multiple missions, run in multiple environments, and for multiple purposes. One of the findings of the study was that EPG required what we called enterprise data management as an enabling technology. The study proposed a simple architectural framework that's composed of data management, product generation, interface, and then a client API library. And this architecture supports RESTful interfaces to data and computational resources. The data management framework supports accessing data at 4 different levels. So it provides 4 different resource interfaces. One, it provides a product level interface to define and categorize and then discover products that are available within data management, a file resource that provides ingest, distribution, and file level searching at the file resource level. Then what we call a file array resource. So with this, with the URL, you can access the internal arrays within the file and just return back the array as a binary stream instead of returning the entire file. And the client library supports either saving that binary stream as a binary file or as just loading it directly into an in-memory variable. The last resource is a data cube resource. This is a virtual or an abstract data structure that provides a way to query the actual science data and then return the result set of that query back in multiple different formats or images. One other aspect of data management that's noteworthy is that we can interface with data partners. So we can catalog and store references to, in this case, an external S3 bucket. So then everybody can come in and search through this interface and do subsetting or whatever through the interface. But we actually don't duplicate the storage. We'll just store references to it and then pull that data in as needed. Our metadata approach was to create a JSON document for each file that's cataloged. And that JSON document has two sections, what we called an EDM core section, which contains metadata attributes that are consistent across all products within the EDM, and then an object metadata section, which stores not only the product-specific metadata attributes, but also the internal structure of the file. So the groups, dimensions, arrays are all stored in that object metadata section of the JSON document. Our product generation framework was built to support controlled integrated software product baselines or algorithm baselines. And those baselines are stored as Amazon machine images. And corresponding to those operational workflow documents, JSON documents can be created and then sent through our integration service API. And the EPG will then use that workflow to interact with enterprise data management to see as data becomes available within EDM, we'll schedule jobs to run the algorithms and then scale out the compute resources based on those Amazon machine images. At least for our need, we have kind of tight latency requirements for operations. What we found is it was better to pre-stage our EC2 instance resources based on the orbit schedules of the satellites that we were producing data for. One other piece of the study that we noticed was that NOAA had a lot of what they called experimental systems. So we categorize this as a boutique federation of product systems. And so we built basically 3 different APIs to support algorithms that couldn't get integrated into that enterprise product baseline. And so the federated approach, a partner or PG system can interact with enterprise data management directly to get the data it needs and then to send back data that it produces. It can use the enterprise product generation as a scheduling service that will register its algorithms and its workflow to EPG, and then we'll receive notifications in the form of job objects so that those jobs can be run on the partner system. And lastly, the partner system can invoke job directly within the EPG. We completed an evaluation. We ran an operational workload for 21 days in the Amazon cloud for 4 different satellites. What we found is that we either met or exceeded operational requirements that reduced costs. One thing we did notice is that the distribution of data out of Amazon Web Services would be the largest cost for the migration of ES-PDFs to the cloud environment. We're looking at making enhancements in terms of containerization of science software, probably including some HPC services, looking at distributed key stores for science data, and also machine learning. And if you're interested, we have a demo video that we created for AMS 2019, and that's it on YouTube if you're interested in seeing more. Thank you very much.
All right. Thank you, Peter. And thank you again to all of our speakers. I'm going to be passing things over now to Zhenlong Li, my co-chair, who will do his own presentation and then close things out here.
Sorry. Thank you, Patrick. Can you hear me now? All right.
Yeah.
Okay, good. So I'm Zhenlong Li. I'm an assistant professor from University of South Carolina. Currently, I'm leading a lab at a university called Geoinformation Big Data Research Lab. So today, I'm going to share with you, briefly share with you a project or system that we have been developed called a scalable online visual analytics system for the big climate analysis. So this system is actually in part funded by the ESIP lab 2 years ago. And now I'm going to show you some kind of function that we have been built, and also some kind of key techniques that we are using here. So basically, the system here is we want to solve a challenge like big data challenge in climate science. I don't want to emphasize this, so there are a lot of data, and it's hard for scientists to use that or to visualize that. And then the solution that we built here is that we try to create a kind of a SQL query and to allow the user to just write a SQL like this here to query to do analysis. For example, if we want to find out the global mean temperature for the last 30 years, we can do a query like this. Select this just like normal SQL here, but we do have some a function that's built in here, and I'm going to talk about that later. So that's the motivation here, and we build a system which is online and backed by the Hadoop cluster, and actually it can run on the cloud. But if we have this virtual Hadoop cluster on the cloud, and the data here we are using the NASA mirror data, which is about 2 terabytes for the land service product, and also some meteorological mirror station mirror data, which is the point data here. So this is the architecture of the system, and you can see here we have this heterogeneous climate data set, which include like array-based data like NASDF here, and also we have point-based data set like the record, like CSV files, and we have spatial temporal indexing. And finally, we have this hybrid query engine mechanism to allow like different query to be plugged into the system. Like currently we have Hive, and we also have Impala, which for the record-based data. And then we have this middleware. Finally, we have this portal here. So the key behind this is, first we developed this space-time variable cube to abstract the data, no matter it's array-based or it's point-based. We can just use the similar way to treat them. So we abstract the data, and then we extended the typical SQL here. Like we extend the SQL to include some keywords here. For example, some visualize ads. We can use different visualization method to show the result. And also we have this area of interest, like region, to allow the users to select the bounding box or area that you want to do the query. And at the back end, we have this also this is part supported by spatial temporal indexing, which is published in a journal here. This is also work with some folks at NASA here about 2 years ago. And then also this is another key technique is grid transformation. So we treat all the climate analysis that as grid transformations that you can just transform. For example, you want to do a query analysis, you can transform this analysis into a series of grid transformations. And then this grid transformation can be further transformed into the map reduce jobs in a cluster. And I'm going to do some demo here, just live demo here quickly to give you a sense of what it looks like here. And this is the project website here, as you can see. And scroll down, there's some information here. And now we have NASA mirror data and some operational data here. And then some function that we built, which this function can be integrated in the SQL to support different query, different analysis. So we have these functions, some explanation and usage examples are also here. And excuse me. And there are several type of functions here. You can just take a look. And then we have some REST API and the web portal here. Let's look at the web portal here. And this is a website that you can just go in here and to do some query here. Let's look at some. I do have some query that's already built here. So let's look at this one. So we have the good thing that you can just create a URL, and once you do a query to bring it up anytime that you want to, or you can share that URL with anyone. For example, here I have this query here to look at global annual mean for last 30 years, I believe. And you can see this query is coming to here, it's here as query, and this result is already there because it has been queried. So the result is cached on the server and it's there. The other one is that we can look at some animation. For example, can look quickly do a global temperature. I believe this is land surface temperature for the last 2 years, actually. This is hourly data. And all the results, as you can see it here, we can look at the result from different perspectives. And I'm going to show you the animation here. It will bring up this animation panel here. So this is the NASA Whirlwind web version here. We can change this speed here, you can see. And then if we stop to one more, you can see. This calculation can be done just within several minutes. And then actually, all the results will be cached on the server, and you can share the whole analysis, including the result, with anyone just using a URL here. Just there is the ID for the query here. So we can do a lot of other analysis here. So like extreme heat analysis, and also look at this anomaly analysis here that I did before. If we just copy this URL here, and if we just put it here, you will see we can look at anomaly of the land surface temperature for the last 30 years. And I do have some documentation here you can see, and then the result is presented as some maps. Okay. And also animation here. So this is a map from 1980. Each year there's anomaly that map that we produced. 1980, as you can see, is here. You can see there are some anomalies. There's a heat wave in 1980 that we captured here. Like 2000. No different year there's a map, this anomaly map, and then you can also animate the whole stuff here over here, and which is this analysis is all done with this SQL style, and which is run at the back end by the cluster, and also the other thing that data we need to process. You don't have to do any further pre-process. You just put data in the cluster and do some indexing that we created, and then the data will be able to be manipulated. And some other kind of analysis here, we can do zoonout statistics based on the point data, and also even including array-based data. And that's it. I think I don't have much time here, and so that's from me. All right, I think this is concluded our seminar today, and I would like to thank everyone that who joined this meeting, and also thank all speakers that you have gave a very excellent presentation that I believe everyone will find it actually found very interesting and useful. And we will continue doing this in the near future, and we will keep everyone updated through our email list and also the wiki page that our group maintained. All right.
Thank you, everyone, and look forward to the recording posted on YouTube as well if you want to review
that will be great. Yeah, we'll post this online.
All right, thank you.
Thank you.
All right. Thank you, everyone. Thank you, Megan.